turn up your volume.
Alright, everybody, this is Shin-Gut, your host of Sg2 on Space, as always. Apologies for the slight delay if you're watching this live. If not, then it doesn't matter for you, right? I should not be saying that. Let's put it this way. Sg2 on Space, hopefully you're watching us on facebook.com/The Shen Show, the one and only. Or you're watching us on YouTube. Simply look up Sg2 on Space and it will be there. It should be there. If not, something's up. Alright, well, of course, we're at the lovely Action One Media studio here. Be sure to follow them on Facebook and check out their website. We are a1.com. If you haven't noticed already, I come here twice a week. I mean, not twice a week, twice a month these days. So the other week, you will see me typically at my place doing a show. All right, just a note for you guys. All right, and be sure to support me, patreon.com/SG2 on Space. I know I keep saying this, probably could use some help. Your support will go towards making the show better. And, you know, you can get awards, get recognition. I will shout out your name, put your names on all the social media outlets. So, might be a good idea. And if you get a higher package donation, you can even have your own spiel during the breaks in the show, which would be great. All right, so this show is typically on Saturday at 1 p.m. these days. Like I said, today it's been shifted a little bit. And, well, without further ado, let's begin. Today, I want to talk about something known as the Holographic Principle, which is, once again, we're going to bring Leonard Kramer on shortly, if he's not already listening. The Holographic Principle, from what I understand, and he will know more, it's actually quite a weird theory in I suppose, physics, that some physicists believe that we might actually live in a hologram. So this is not even a real reality, which isn't that we're some kind of fake simulation out of, say, the Matrix. So not saying that at all, but rather that whereas we seem to live in this three-dimensional universe, we're actually maybe a projection of two dimensions. All right, so this is what's known as a holographic principle. All right, and if you look into the mathematics, it can get really complicated. Maybe Leonard would talk about that a little bit. But the thinking essentially goes like this. So some distant two-dimensional object, a distant two-dimensional surface, contains all the information needed to fully describe our universe. And like a hologram, this data is projected to appear in three dimensions. I don't know if you guys have seen a hologram. Nowadays, you have these virtual reality or whatnot machines and so forth, and some other stuff. You can actually even just create it out of mirrors. So, but point is, you know, you have this. It's actually a two-dimensional thing, but it creates this three-dimensional image, right? All right. Now, this may sound pretty far-fetched, but why do scientists even want to consider that? Well, it's because a lot of the big physics problems, such as nature, black holes, and how to reconcile, as I have said before, gravity, one of the four fundamental forces, is the only force that can't seem to be reconciled with the other three, and it doesn't. Gravity, as we know it now, is perfectly described macroscopically by general relativity, but it's not able to be reconciled with quantum mechanics, which is in the very small, right? However, if you're doing this holographic projection, holographic principle, then these problems are much easier to solve. So it makes more sense, it seems to make more sense when the laws of physics are applied to 2 dimensions rather than 3. Who formalized this idea? It's funny. This was another Leonard. Leonard Susskind. Susskind? Susskind. A Stanford physicist who first defined this idea several decades ago, and it has become a working tool to solve problems in physics. However, that's not to say that our universe is actually a 2-dimensional hologram. Calculations, saying you can do calculations one way to simplify things, does not mean that it reflects actual reality, right? But it's a suggestion. It's an intriguing. I wouldn't call it a recommendation. Intriguing possibility that our universe could be a hologram. All right, so let's see if we can bring Leonard on to talk about it some more. Leonard, are you on?
Yeah, I'm here. Can you hear me all right?
You're loud and clear. Your voice is well, your voice is yourself as always.
Yeah, I'm stuck in traffic right now.
I was stuck in traffic. That seems the norm here in Houston, for sure. All right, so
yeah, it's getting to be kind of not a very user friendly city.
It's a terrible.
Anyway, carry on.
Mm-hmm. All right, so let's just jump into our topic today, because I didn't even know what this was. So, you brought it up, holographic principle. I briefly looked at it and I thought, wow, intriguing. I've never thought of that. Can you tell me why? Well, first of all, let's ask you, in your words, what exactly is it?
Well, a lot of there's an increasing number of physicists who are interested in this idea that all of the information that is contained inside the universe is actually projected onto a surface that's at the boundary of the universe. And it's in analogy to studies of black holes, which we've talked about before. Before Stephen Hawking, there was a physicist named Bekenstein, and he was studying entropy and the thermodynamics of black holes. And so what he discovered was that there's a kind of a mathematical law of looking at general relativity, where the surface area of the event horizon for a black hole grows in proportion to the mass, and the mass has an energy equivalent. And so what he noticed was that the ratio of the mass to the area resembles the thermodynamic formula for entropy in thermodynamics. The equation there is the total amount of heat divided by the temperature is this quantity called entropy. So he noticed that they were in kind of they looked a lot alike, and so he came up with this idea that the entropy that's what the entropy is. So it's entropy is proportional to the surface area of a black hole. And then the other thing is that no matter what you do to a black hole, right, it increases in size. It either stays the same or it increases in size, which is kind of what entropy is. Now that's paradox.
Okay, are you? Hey, did you cut off, or are you still there? Hello? Can't seem to hear you, Leonard. Okay, well,
Things are falling into it, right?
I'm sorry. Can you say that again?
idea about a black hole was that it only needed three things to describe it. It had total mass, spin, and electric charge.
Right.
And so there's very little information. So there's this paradox that all of this stuff is falling in, and this is important to the details of how physics, of some elements of physics. All of the things that are falling into it have information, and so it goes from a lot of information, and then it falls into the black hole and disappears.
Right.
So it goes from a lot of entropy to no entropy, or virtually no entropy. And so that was a big problem, and
yeah, that is really strange. I believe this is called the black hole information paradox, and Stephen Hawking came up with it, which essentially meant that. All right, so I think Leonard dropped off, so let's possibly take a short little break. We'll be back. Hopefully the connection works better, which he is driving, makes sense. So, all right, we'll take a short break.
You know, some of the other things you got going on.
Absolutely. So thank you for having me. I feel like I'm in the presence of like celebrities. Y'all real fans to me.
It's just a shades, man. It's a shades.
So I think like 2000.
And we are back. This is Shinga.
we are back.
Hello?
We are back.
I know. Thanks, Leonard. I was actually saying that. We're back on Sg2 in Space after our very miniature break while we were getting Leonard Kramer back on. Today we're talking about holographic principle / holographic universe theory. All right.
Right.
So, talking about black holes. Go ahead.
Yeah. So we're kind of talking about black holes, and hopefully we can get to the why it's a hologram. So all of this information is falling into the black hole, and then it just apparently just disappears, which is a no-no. That's a physicists choke on that. And so what Bekenstein observed was that all of this information was disappearing, and then Stephen Hawking came along in '74. And he played around with his equations too, and discovered that the black hole has a temperature and will radiate. So if it has temperature and radiates the Hawking radiation, then that means it has entropy also. So the information, it was a problem for a while, and then in the late '90s, I think, or mid '90s, there was a physicist. I think he was from. I don't want to say where he was, and he has an unusual, strange name, which Devoot or something like that.
And so he's Dutch. Gerard Hooft, Hooft.
There it is, yeah. And he and one of my favorite professors on the internet, Leonard Susskind, came up with this notion that all of the information having to do with objects falling into the black hole up here on the surface. In other words, because you're so deep down into a gravity well, everybody's seen Interstellar, right?
Yes.
So where they go down, and so time is going very slowly. Time is going slowly from the vantage point of the poor guy on the spaceship. So 20 years goes by for him, and only 45 minutes goes by for the dudes on the surface. So that's like a real thing. Okay, that's actually a real thing. You can see redshift of objects that are orbiting close to black holes, and that's their time going slower, right? something falls into the black hole, it just from the vantage point of outside, time keeps slowing down, right?
Mm-hmm.
And it just gets slower and slower and slower until it virtually stops. Also, everything gets distorted, so everything gets all swimmy around on the surface of the black hole. It gets very dark. So this, what's his name? Van Hoot?
Yep.
Did I say it right?
Hooft. H-O-O-F-T. Hooft.
Hooft. Yeah,
Hooft.
Hooft. We got to do this right because it's we're supposed to
pronounce scientists'
supposed to
name
know
right.
these
Got
things.
it.
Yeah, we're supposed to pronounce things right. So everything's on the surface, right?
Yeah.
And if you try to get more stuff in, then it just gets bigger. And ultimately there's an incredibly tiny pixel. It's called a Planck area.
Mm-hmm.
And I don't know the exact, I think it's something on the order of 10 to the minus 34 meters
10
squared.
So close. Well, the Planck length is 10 to the negative 35th meters. It's like
okay, so the Planck length, the Planck area would be like the exponent would double, right?
Yeah,
twice as much.
So you're right, pretty much.
So that's the Planck area, and that's the ultimate smallest area. And that's the pixel. That's sort of like the pixel. And if you try to put more stuff into a volume, it'll just make that area grow. Make the area grow.
Mm-hmm.
And so this is an intriguing idea that the surface of the black hole
Mm-hmm.
has all the information associated with everything that's ever fallen in. Everything that's fallen in is gone, but the gravitational effect of everything that's on the surface that's fallen in is still impressed on the surface. And so the Hawking radiation, which contributes to the decay of the black hole, gets moderated by all of the by the gravity of everything that's ever fallen in. So the surface, so it's not true as Hawking pointed out that the entropy of the black hole is just three numbers. Spin, charge, and mass. It's also spin, charge, and mass, and all of the little wiggly gravity perturbations that are on the surface from everything that's ever fallen in. So when the Hawking radiation comes off of in particles from the surface, they're pushed or pulled in proportion to the objects that have fallen into the surface, and so that resolves all of our problems with thermodynamics. It's kind of neat. It's kind of cool, but some people have extended this, and I think I'm getting more and more comfortable with the idea that everything in the universe, I'm right downtown Houston right now, and I'm looking at the skyline. I see all these buildings and all the information that's encoded, and everything, all the planets, all the galaxies, and everything have information, and that information originates on a surface, or it's entangled with a surface that is 14.7 billion light years away.
Mm-hmm.
And some people are starting to get comfortable with this idea that the ultimate reality to the universe is not the objects that we see. It's not the traffic I'm in right now. It's something that's moving around on that surface way out there, right?
So reality is not you in traffic. Got it. Go on.
What?
I said that was a good one. True reality is not you stuck in traffic right now. Go on.
That's right. But that's the holographic principle, and I guess people can go ahead and look at Leonard Susskind's videos on that subject to learn more about it.
Let me ask you
this.
Sorry to interrupt. So we were talking about black holes for a second. And then somehow this just extends to talking about the whole universe.
Oh, you noticed that?
How does that? Yeah.
Well,
like why?
Well,
How do you just
okay, so the
generalize?
surface of the black hole is sort of a boundary that separates everything that's fallen into the black hole with everything else in the universe. It's a boundary. Well, there's another boundary that resembles it, but it's sort of in the inverse sense. The universe is expanding, and so from everyone's point of view, that expansion extends out 14.7 billion years to the point where the expansion is equal to the speed of light.
Okay,
There's not
yeah,
a problem with this. Things beyond that are actually moving away from us faster than the speed of light. Okay, now everybody's going to freak out. No, nothing can travel faster than the speed of light. Well, this is the actual expansion of space.
Yeah.
So it's the actual space is moving away at faster than the speed of light. So that's utterly elsewhere. We don't have any access to that. But at that surface resembles the black hole, but in the inverse sense. In other words, at that surface where the expansion, the Hubble expansion is equal to the speed of light, we have a similar effect, or a parallel kind of effect, where all of time slows down for objects that are exiting, or photons, or any of the information of everything inside. So it slows down and stops at that surface. So that surface is effectively a hologram for everything that's inside the universe.
Okay.
So
All right.
I'm hoping that you think that is as wild as I think it is.
I think that's pretty nuts. So I see the analogy now. Now in terms of actual, do you think, what is the advantage of this over our conventional theory, let's just say? Do you happen to know?
Well, I mean, it's not that it's a matter of it being an advantage. It's a matter of what is the nature of the universe. So it's not like I'm going through looking at theories and then picking the one that's most advantageous, right?
Yeah.
I'm saying that could be the ultimate reality. So that the things that we see and all the atoms that make up our body do seem to have a counterpart at some level on this remote surface. We can't actually view this surface because it's what we see, or what we ultimately would see of that surface is 14.7 billion years ago. But there is a now, there is a reality now, and it corresponds to objects, or motions of these little pixels that I mentioned, Planck area pixels that are moving around, corresponding to the fields that make up all of the particles in the universe.
Let me jump into something. Okay, do you happen to know a way of actually showing, like experimentally proving this?
I don't know. I'd have to think about that some more.
All right.
Just relating to you what physicists are starting to become comfortable with this idea, and I just think that it's interesting. And I'm not making this up. It's like go and string theory has something to do with it as well. So maybe we should try to have a look at that and talk about that another day, because string theory connects to this. I have problems with string theory and dark matter and dark energy.
Yeah,
but that's for another day.
That is for another day.
Yeah.
I was wondering about if you knew more about these potential these experiments, because I was just reading here that Fermilab built something called a holomotor, HOLOMOTOR, to because some physicists believe that the holographic principle predicts there's a limit to how much information space-time can contain, because our 3D space-time is encoded by the limited amounts of 2D information. So,
Right.
so what
So
that
it
means,
seems strange. Yeah,
Mhm.
it seems strange that the information is related to the surface area of a volume, because you're thinking, well, there's a whole lot more volume in than there is surface area. But what happens what happens is, as you try to put more and more information in there, the gravity gets the gravitational distortion of the of the of the things that you're trying to encode into it get too close together, and then it collapses into a black hole. So that's the ultimate. That's kind of like limit. That's why it's on the surface. Why the surface is important rather than the volume. If you try to put too much stuff into a volume, then it collapses into a black hole, and that includes anything that you would try to encode, encode bits of information. That was what Bekenstein was alluding to, and so the reference to particle accelerators. In order to test these things, we would need huge, much bigger particle accelerators that could create black holes, essentially.
yeah,
Which sounds scary, but like microscopic black holes are manageable because they radiate, they disappear on their own. But,
that does sound kind of crazy, though. Now, from what I'm reading about this experiment, they're just like using interferometry to see if there's a fundamental limit to storing information in space-time, which is kind of cool. But apparently, your favorite physicist, Leonard Susskind, okay, maybe not your favorite physicist, one of yours, he
Yeah.
rejects. He does not believe this experiment will prove anything. So, who knows?
I don't know.
Yeah. Now, going back to the philosophical nature, let's just say that we show somehow that we are living in a hologram. Is that going to affect your life? Or what are we going to do differently?
Well, helps me appreciate the traffic better.
To know that it's not a real traffic.
It's not real. It's out there 14.7.
The traffic is just a projection
away.
from 14.7 billion light years away. Got it.
So it also may have some relationship to quantum entanglement and what they call non-locality, which maybe we talked about before, which is the everybody likes to call it spooky action at distance,
right?
Which was made Einstein so uncomfortable.
Yep. Einstein.
And may also have some relationship to some other philosophical things we've talked about, like whether reality, whether the future exists in the same sense that the past exists, in which case the things all the decisions and all the things that are to happen already exist in some sense, but that's getting way out there.
If the 2D encoded information, are you saying already contains future data? I don't know if that's what you mean.
I'm not saying that. I'm just saying that it helps us make progress toward those kind of questions.
Got it.
What we don't understand the quantum mechanics when gravity is involved. So we don't have physics. We don't have a quantum theory of gravity, and so people have started to think about once again to think about what quantum mechanics means. It used to be that they just when we were growing up and learning quantum mechanics in third grade, um, it was just, look, it just works. So shut up and calculate. But in order to make progress with quantum gravity, which we need to understand, like things like the Big Bang, the origin of the universe, because the origin of the universe and the Big Bang, everything in the universe is stuck together, is crushed together at a point, and so we don't know what that's all about. And in order to make some progress, we need a theory. So thinking about the nature of the universe and the nature of reality seems to be important to that. I think it is. I mean, when I was learning quantum mechanics, it would drive me crazy because the professors, would never talk about that. It's just a mundane thing that you calculate, and it gives you the right answers. It's a fabulously useful and correct theory.
Right, but then they never explain, hey, why this works, and they don't go into that. They're just like, go calculate.
Yeah.
That makes sense. Now, I've never heard of the holographic principle at school, and I studied physics as well as one of my majors. Is this not something which is mainstream right now? I'm curious.
Well, it's starting. It's within the past 20 years, people have started to believe it. Certainly, it explains a lot of things about the nature of the black hole. Mm-hmm. It resolves the entropy. It resolves the Hawking's objection, because Hawking just wrote his papers in '74 and said, well, look, the entropy disappears. Deal with it.
Right.
It just does, and it could have been like that, but Von Hooft, resolved that by thinking about by thinking about it
right.
Theoretically. He came to that conclusion, and I think it's right. And also, so Hawking said there was entropy in a black hole because it had temperature.
Yeah.
Right.
Yeah.
And then Bekenstein just was playing around with equations and said, hey, this looks like entropy, which is information, right? This looks like entropy, and those two things kind of gave the same answer, which is like satisfying.
Let me ask you one other thing before we eventually conclude this program. But let me ask you this: so, is there a connection between all this physics stuff and information theory from like I guess I don't know if that's computer science or something. Do you happen to know?
Yeah, I mean that is kind of from computer science. Yes, but I'm not really up on how what to say about that.
Well,
I don't know. But we can have a look at that and see what we can learn about that.
Well, I know from my just random interests in reading stuff is that in information theory there's something known as information entropy, which is essentially the well, actually, it's interpreted as the average rate at which information is produced by a source of data. So, I don't know. I mean, apparently this definition of entropy used in information theory is directly analogous to the one in statistical thermodynamics. And the guy Bekenstein that you mentioned, he actually described a previously unexpected connection between information theory and classical physics. So, but in any case, we could look.
All things are information. Everything is information.
Right.
And so we can make some progress along those lines. But it means if that's the case, then it can be mapped back to this surface that's 14.7 light years away.
Okay.
And 14.7 billion light years away.
Man.
Okay.
Hey, Leonard, how you doing? This is Atum at Action One. Always appreciate the conversations. I have a quick question. Just listen in on this, and I want to ask your opinion on Professor James Gates and his theory about the universe being a series of zeros and ones, kind of like computer code, like the Matrix. I just wanted your opinions on Professor James Gates' theory.
Well, that's kind of what we're talking about. We're talking about a zeros and ones that reside on that surface of the that surface that's 14. I don't know exactly what to call the surface. I think they call it like a de Sitter surface or an inverse de Sitter surface. But that's what we're talking about. But I'm not an authority on Gates.
I think he works on like supersymmetry and things of that nature and string theory, which is, sorry, I don't know how it's related to holographic principle, but is string theory somehow related to this too, right, Leonard?
Yeah, well, I think we should save that for another day and talk about that fine. Because that's actually kind of like part 2 of this discussion.
Part 2. Yeah, we can probably talk more about what Gates came up with then. So I was actually going to say that the other physicists you really appreciate, Jacob Bekenstein, in terms of entropy, he actually said that the thermodynamic entropy and the Shannon entropy and information theory are actually conceptually equivalent. So the number of arrangements that are counted by Boltzmann entropy is I guess proportional to the amount of Shannon information, which is kind of weird.
Right. I'm only vaguely familiar with Shannon's principle.
That's okay.
You can go on YouTube and find some lectures.
No doubt you can. Yeah. Of course. That's all good. All right, are you still in traffic?
No, I'm waiting to do my drum circles.
What is that?
What's a drum circle?
What is that?
It's like a new age kind of thing that I've been doing lately. I go to this place in West Houston, and I get together with about 24 other people, and we play drums, and we become connected holistically together, and so it kind of takes an organic shape to it.
So you guys just gather together in a circle and play drums. This one's at a church. I forgot the name of the church. I can't see their sign,
but I'm just waiting in the parking lot, and I'm going to go in and drum, do some drumming. They're waiting for me, actually. I'm the star. I'm not.
Wow, that's pretty funny. Drum circles.
Yeah.
Never heard of that. I learned something new today too. Another one. Go on.
Yeah. Well, that's all. I'm gonna go do my drum circles. And it's like I'm half hour late, but that's your fault.
Wow, blame it on me. All right, I'm not gonna pass along the blame, although I could. So let's not do that. I'm gonna blame it on traffic too. How about that? I'm gonna throw it.
Okay.
All blame is on Houston traffic. There you go.
It is Houston traffic.
Thankfully, it's not real. It's a 3D holographic projection. So
that's right.
So if you keep that in mind, you're not gonna be stressed out by traffic. It's like.
You won't be. Did you know Texas is the orange barrel state?
Wait, what is that?
Well, if you drive around, you're going to see orange barrels everywhere because there's so much construction, and so that's something that occurred to me the other day.
Got it.
The Orange Barrel State.
All right, that's. I thought that was actually a name for that. Got it. All right,
Yeah.
Leonard, I'm gonna not have you. You can go and do your drums, unless you have some other riveting thing you want to say now.
What are we doing? We're looking up in the sky for some. Is that how we end the show? It's like keep looking to the sky because Lucy's there, in the sky with diamonds, and the acronym for that is LSD. Is that what they said? Hey, it's the Beatles. Come on.
Yeah, there you go. Well,
you know who the Beatles are, don't you? Where?
Yeah, of course. So that's all good. You can drop off. I will finish the show. And
okay.
All right. You have fun drumming.
Thanks, Chen. Stay in touch.
All right, of course. So with that, bye, Leonard. Speaking of UFOs and such, I actually have not talked about that, but it's interesting because there's a notion that hey, all these people are just nuts, or okay, conventional people. For me, I'm like, hey, they're already here, and then the question here might be, well, like, where are they? What are they doing? My view is, well, if you're a super advanced, intelligent species, you don't want to disrupt the status quo, although maybe our status quo kind of sucks in many cases. But still, you're like, let's observe and see, just let the civilization progress, kind of like in Star Trek, I guess. But point is, I've often wondered, in some sense, why people who look at UFOs, ufologists, that's what they call themselves, are not considered legitimate versus scientists who, for instance, there's an organization called nonprofit called SETI. I may have talked about them before, the Search for Extraterrestrial Intelligence. They are considered legitimate scientists since they point telescopes at the sky and are trying to detect signals, right? And they are looking for electromagnetic transmissions, and so they are. So far, have they found anything? No, they haven't. So, in any case, now they have been considered now, like, what do you call it? Kind of taboo, in a sense, even though they're legitimate scientists, and but they're still considered more legitimate than, say, ufologists. All right, now SETI scientists, as well as scientists from other works, have kept their distance away from ufologists because they don't want to get contaminated by this. Oh, we're just all believing aliens are here, they're flying. Come on, we're scientists. We don't believe that stuff. Well, the reason it turns out that the study of UFOs, according to an article I recently read on Wired, it is not considered a legitimate scientific study, at least some academic researchers say, is because there's not enough hard UFO data. UFOs are by nature not permanent. They're ephemeral. And what does exist is dependent on, quote-unquote, unreliable personal accounts. All right? There's no systematic plan of investigation. Ufologists have no theoretical framework of describing how aliens could build spaceships and then come here and behave the way observers claim, or how they can get here and all that. And then, considering the fact that a lot of UFOs do have rather mundane explanations, like airplanes, military projects, some atmospheric phenomenon. However, if you really want to know, this is actually not always been the case. In fact, in the early 1950s through the 1970s, a lot of scientists actually took the study of UFOs seriously, and they regularly engaged with ufologists, all right? Back then, the military had open UFO research program. Okay, still, they were still classified, but people knew about them, all right? So the military deemed them worthy of study, even though the investigators typically came up with nothing to see here, right? So those programs ended. For instance, in 1968, the Air Force ended it, and then the ostracism, where it's like, stay away from me, ufologists, that's when they began, right? So, and then it became like these fringe people who are crazy and nuts and all that. All right. So it's kind of like the scientists who are, okay, so in high school, for instance, bad analogy, but I was not a cool kid. All right. So it's like the ufologists are now like the losers. They get out there. They're weird. All right. Don't sit at the cool kids table. All right. So, yeah. I mean, it's just categorically dismissed. Like legitimate scientists, legitimate, quote unquote. Actually, a lot of them are legitimate. I mean, they just don't. They're like, okay, you're gonna talk about UFO research. We're not even gonna look at it. Forget that. Don't give me this stuff. All right. And any case, so it is really unfortunate, in my view, that this is how it is right now. I think what's happening is that the government, and I'm not a conspiracy theorist, I'm not going to say that, but it would seem to make sense to me that why would you suddenly terminate research, right? I mean, our government has done all sorts of weird things, like looked into like mind control and telepathy and stuff like that. That's just like, may sound like nuts. So clearly our military and secret research programs have looked into stuff which, like, quote, like, how should I put it, legitimate, your average professor at a university or research organization, institution, they're not going to touch that. They're like, but our government has looked into it. Why? Because why would you spend millions, maybe tens of millions, hundreds of millions of dollars doing stuff like that if you don't think there's some legitimacy to it, right? And are they just suddenly just going to give up, like 1968, right? The Air Force, like, oh, we're done. We're not. Okay, we haven't found anything. Possibly, but I think really it just went more black, so to speak, in terms of black projects. So because I think what ended up happening is that they did find something. You could have 99.99% of the time not finding anything, but if you just have that 0.00, even 0.01% of finding something that can't be explained, and you got something legit, well, do you want to reveal it to the public or just say we haven't found anything? You're probably going to be like, oh, we didn't find anything. We end the program. And as a lot of us know now, the Air Force actually, or the Pentagon, never really closed the door. I mean, just, 2 years ago, it was revealed that there was a secret program on some floor of the Pentagon, which they were spending money investigating UFOs still. All right, and that I think might just be the tip of the iceberg. No doubt there's other agencies in the government or whatnot that's working on stuff like that. All right, that's my perspective. All right, with that speculation aside, so we talked about holographic principle, which is all reality is not reality, or rather it's 2D projection, to UFOs. One day, I would hope to ask our local alien, local extraterrestrial intelligent scientist, all right, because I'm pretty sure they're not all aliens are smart. That's just how it is. I mean, look at all humans, right? so let's take an intelligent extraterrestrial species, alien person, whatnot, and be like, hey, so what do you think of our physics? Like, is this true? Did you show that we're actually living in a hologram? That'd be cool. But in any case, all that rambling, bumbling speculation aside, we shall see what will happen, right? Okay, I'm going to conclude it here. Still sitting in the Action One Media Group. Thank you for providing the studio, everything. You've been listening to SG2 on Space. Be sure to follow me at facebook.com/TheShen Show, THESHEN Show. All right. And subscribe to me on YouTube. Look up SG2 on Space. It's fairly easy. Nobody else has that name. And Once again, I will say this. Support me on patreon.com, patreon.com/SG2 on space. I will put out more things so that you guys could actually enjoy this program more. All right. In fact, I'll do it even before getting support. But point is, feel free to support me. I can call out your names. You can even get a what do you call it? A segment, or your words on the show in between segments of the show. All right. So with that aside, as Leonard was saying, he could not remember what the catchphrase is, but I will tell you guys right now. Look up, because you never know what you will see. All right. Be sure you do that, even if it's cloudy. All right. Take care, guys.
Peace, it's Brother Atum Ra, and you tuned in to Action One Network.